All right, welcome back. This next video will be on chapters 14 and 15. Chapter 14 and 15 will be basically reviewing all of those old probability rules that you learned when you were younger. So there's really not a lot of notes per se. I have one slide of notes, and then the rest of the slides in this PowerPoint are just examples. And then I will go through some of the questions from Math Excel as well. So just to review for our formal probability rules, um, a probability has to be a number between 0 and 1. You can't have a probability, you can't have a negative probability for obvious reasons, and then you can't have a probability that's greater than 1 because that would imply that there is a greater than 100% chance of something happening, which we of course know is theoretically impossible. And then the probability of the set of all possible outcomes of a trial must be 1 or 100%. Okay. A coin flip, if I add up the probabilities of each outcome 50-50, I get 100% or 1. So what that requirement is saying is if I add up the probabilities of each individual outcome, I have to get 1 or 100%. So a couple of the rules that we have for probability that you should know already. One is the addition rule. Addition rule applies to OR probability. So this is some fancy notation, but basically what that's saying is if I want to find the probability of one thing or another thing happening, then I basically add up the original probabilities, the individual probabilities, and then subtract out the overlap. So if I want the probability of one thing or another thing happening, I find that probability by adding up the individual probabilities and then subtracting the overlap, meaning that, for example, if I wanted to find the probability of having a red card or a 5 in a standard deck of cards, the overlap in that case would be that there could be a 5 that is a red card. There would be some overlap between the number of red cards and the number of 5s in the sets. So that's what I mean by overlap. And the reason we subtract the overlap is to avoid double counting. Like I said, in the example that I gave, there are 5s that are also red cards, and you don't want to double count in order to ensure the most accurate probability. Now, there are cases where there aren't overlap. So if you have two things that what we call are mutually exclusive means two things that can't happen at the same time. Well, if they can't happen at the same time, then there will be no overlap. So go back to the deck of cards example. If I wanted the probability of having a 5 or an ace, those two things, 5s and aces, would be mutually exclusive. There are 4 5s and 4 aces in a deck of cards, but there isn't it isn't possible to have a 5 and an ace. So there's no overlap in that case. So that's our addition rule. Our multiplication rule is for end probability. So if I wanted to find the probability of one thing and another thing happening, I would multiply the individual probabilities. Now, this rule only works if the two things are independent. And independent means that one result doesn't affect another result. The classic example I give is with coin flips. Coin flips are independent of each other. If I flip a coin 5 times, that the result of the first flip of the coin is not going to affect the result of the second flip or the third flip, etc. So this multiplication rule works for independent things. Okay. This slide right here is really the only notes we have. Really, the thing with these two chapters is just doing examples. So, like I said, the rest of the slides here are just examples. So let's start going through them. This is an example I took from the textbook, and we're going to use for a few of them here. So a consumer organization predicts that over a 1-year period, 17% of cars will need one repair, 7% will need 2 repairs, and 4% will require 3 or more repairs. So what is the probability that a single car chosen at random will need no repairs? Okay, so this is kind of where that addition rule is going to come in. I know that 17% need 1 repair. I know that 7% need 2 repairs. And I need 4%. I know 4% need 3 or more. Okay. If I add all that together, that's 28% total. So 28% need 1 or more repair. So how am I going to find the percent that need no repairs? I'm simply going to subtract 28 from 100, and I get 72%. So 72% of cars, according to this example, need no repairs. So we would say that the probability that a car needs no repairs is 0.72 or 72%. When you do questions like this in Math Excel, what you're going to want to watch out for is if they want it as a percent or a decimal. If they ask for the answer as a percent, then the answer is 72%. If they ask for the answer as a decimal, then the answer is 0.72. So make sure you pay attention to that, especially in Math Excel. Second example, we're going to use the same information. Now we're going to ask is what is the probability that a single car chosen at random will need no more than 1 repair? So the key in this case is no more than 1 repair. So the question is, does no more than 1 mean 1 or more or 1 or less? No more than 1 means 1 or less. So we saw that's a typo, that should say example 1. Our example from the last question, we determined that 72% of cars need no repairs. And we know from the question here that 17% of cars need 1 repair. And if I add those together, I get 89%. So 89% of cars need no repairs or 1 repair. In other words, no more than 1. Okay? So this is where that addition rule is coming in. Third example, same information. What is the probability that a single car chosen at random will need at least 1 repair? So instead of no more than 1, we're doing at least 1. Now, at least 1 means 1 or more than 1. So this goes back to our information. We know that 17% need 1. We know that 7% need 2. And we know that 4% need 3 or more. If I add all that together, I get 28%. So the probability that a car needs some repairs or more than 1 is 0.28 or 28%. Okay. Next example, same information. Okay. If you own 2 cars, what is the probability that neither will need repair? Okay. If you own 2 cars, what is the probability that neither will need repair? So in this case, we want to know the probability of 1 car and the second car not needing repair. This is where that multiplication rule is going to come in. So we know that 72% of cars need no repairs. That was our first question. We figured out that 72% of cars need no repairs. So we know that the probability that the first car doesn't need a repair is 72%. Okay. I also know that the second car, the probability that the second car doesn't need repair is 72%. So to find the probability of both of these things happening, the first car and the second car not needing repair, the key word there being and, I'm going to multiply those things together. 0.72 times 0.72. If I multiply those things together, I get 0.52. Okay. Fifth example. Okay. If you own two cars, what is the probability that both will need at least one repair? Okay, so we figured out that 28% of cars need at least one repair, one or more. We figured that out in a previous question. So the probability that the first car will need at least one repair is 28%. And then independently, the probability that the second car needing at least one repair is also 28%. All right, and just like in the last one, excuse me, we're going to do the same thing, but instead of 72 times 72, we're going to do 0.28 times 0.28, and we get 0.08, or approximately 8%. Okay. Let's look at the sixth example. Now we're going to switch it up. Okay. A junk box in your room contains a dozen old batteries, 5 of which are dead. You start picking batteries one at a time and testing. Find the probability that the first 4 you pick all work without replacement. The key in this case is without replacement, meaning I pick a battery at random from the box, I check to see whether it works, and then I put it off to the side. Then I pick a second battery out of the box, and I test to see whether it works, and then put it off to the side. Okay? So the key in this case is that there are a dozen total batteries. Okay, a dozen is 12. And I know that 5 of them are dead. So if 5 of them are dead, and there are 12 total, then I know that 7 out of those 12 still work. Okay? So the probability that the first battery is a good battery is 7 out of 12. 7 of the batteries are working, and there's 12 total. 7 out of 12. Now here's where it gets a little tricky. The probability that the second battery is good is only going to be 6 out of 11. Because if I pick the first one and put it off to the side, and I assume it's a good battery, then there's only 11 left, and out of those 11, 6 are good. Okay? Probability that the third battery is good is going to be 5 out of 10. Again, because this is without replacement. Okay? And if I continue, the probability that the fourth battery is good is going to be 4 out of 9. Okay? And the way we find the overall probability is to simply multiply all those fractions together. And when I did this, I literally put these fractions into Desmos just like this. 7 out of 12 times 6 out of 11 times 5 out of 10 times 4 out of 9, and I got 0.07 as an answer. Okay? The key with this is without replacement. Okay? Let's do one more example. There's one more example in this PowerPoint with the batteries. This one's kind of tricky. Find the probability that you have to pick 5 batteries in order to find one that works. So what they're saying is that you're picking batteries at random and testing them, and they want to know what's the probability that you don't pick a good one until the 5th try. Okay? So if you don't pick a good one until the 5th try, then that means that the first 4 are no good. First 4 are dead. So if you don't get a good battery until the 5th try, that means the first 4 are dead. Okay? So the probability that the first one is dead is 5 out of the 12 total. Okay? Probability that the second one is dead is 4 out of 11. And we can continue this. Third one is dead would be 3 out of 10. Fourth one is dead is 2 out of 9. But then on the 5th try, we get a good battery. So for the 5th one, We want the probability that the fifth one is good. Now there's only 8 left, okay? Out of those 8, we know that 7 of them are good because on the 5th try, we get a good battery. We haven't used any of the 7 good ones yet. So 7 out of 8. And to find the answer, I literally go into Desmos and I multiply all those fractions. 5 out of 12, 4 out of 11, 3 out of 10, 2 out of 9, 7 out of 8. And I get an answer of 0.009. So you can see it's a very low percentage. It's less than 1%. What that means is chances are you're going to get a good battery before the 5th pick. Okay. So again, the key with this one is without replacement. Now in this question, notice it didn't say without replacement, okay? What I am telling you is in MathXL, anytime you do an assignment, all right, and you're picking things at random, all right, what I'm telling you is to always assume it's without replacement unless it's stated otherwise. I'll say it again. You always assume that it's without replacement unless it specifically states otherwise, which is why I assumed without replacement in this example here. Okay. Now that's the end of the PowerPoint. Now what I'll do for the rest of this video is I'll go and I'll do the questions from chapter 14 and 15 on that MathXL assignment. Let's pull up the MathXL assignment here. There are 10 questions on the chapter 13 through 16 assignment. Now, I went through the first couple, in the chapter 13 video, and we determined that questions 1 and 2 have to do with chapter 13. So I'm not going to go through those again. I already did those. Questions 3, 4, 5, 6, and 7 have to do with chapters 14 and 15. So I'm going to start with number 3, and I'm going to go through questions 3 through 7 right now. Okay, so this is our cars needing repair section. Okay. Notice in here, there's no percent symbol, so we're going to assume that they want decimals here, okay? So a consumer organization, so we have 16% need 1 repair, 10% need 2 repairs, 3% need 3 or more. So the probability that a car will require no repairs. So we're going to do exactly what we did before. So 16 need 1, 10 need 2, 3 need 3 or more. So 16 and 10 is 26 plus 3 is 29. Okay. And then if you need to use a calculator, use a calculator. 100 minus 29, that leaves us with 71% left over. So that means 71% of cars need no repairs. Okay. The probability that a car will require no more than 1. Okay, again, no more than 1 means 0 or 1 or less. So we know that 71%. Okay, we know that 71% needs 0 repairs, and we know that 16% need 1 repair. So that gives us 87% total, or 0.87. Okay. The probability that a car will require at least 1 repair. Okay, at least 1 means 1 or more. So 16% need 1, 10% need 2, so that brings us to 26%, and 3% need 3 or more. So 16, 10, and 3 is 29%, so 0.29. Okay. Let's see. For a certain candy, 10% of the pieces are yellow, 15% are red, 5% are blue, 20% are green, and the rest are brown. If you pick a piece at random, what is the probability that it is brown? So We have 10. 10 plus 15 is 25, plus 5 is 30, plus 20% is 50. Okay, let me double check that I added that up right. 10, 25, 30. Yep. So we have 50% total, and we know that the rest are brown. So that means there's 50% left over, or 0.5 for brown. Well, what do we want next? We want the probability that it is yellow or blue. Well, let's see here. 10% are yellow, 5% are blue. 10% are yellow, 5% are blue, so that's 15% total, or 0.15. Okay. Number 5. For a certain candy, 5% are yellow, 5% are red, 15% are blue, 10% are green, and the rest are brown. If picking is done with replacement, and if you pick 3 pieces in a row, what is the probability that all 3 are brown? So let's determine what percent are brown. 5%, 5 and 5 is 10, plus 15 is 25, plus 10 is 35. So 100 minus 35 is 65%. So 65% are brown. We want to know the probability that the first one is brown, and the second one is brown, and the third one is brown. So if I assume that's with replacement, excuse me, then I'm going to just multiply those 3 probabilities together. So it's going to be 0.65 times 0.65 times 0.65. That is our answer. And let's make sure we round to the correct number of decimal places. It says round to 3 decimal places. So that's going to be 0.27, and that's going to round up. So 0.275. Okay. Number 6. Okay, let's pull up this table here. Okay, actually, we can see it. Probabilities that an adult man has high blood pressure and or high cholesterol is shown in the table. What's the probability that a man has both conditions? So that means they have both high blood pressure and high cholesterol. And according to this table, it looks like it's 0.19. Okay, 0.19 is both high blood pressure and high cholesterol. Okay. The probability that a man has high blood pressure, so just high blood pressure. So you could have high blood pressure and high cholesterol. You could also have high blood pressure and okay cholesterol. So the probability of high blood pressure is this whole column here. So that's 19% plus 16%. So 19 plus 16 is going to be what? 35? Okay. So 0.35. And the last question for this chapter is the batteries question. So we have 15 batteries and 7 are dead. So 7 out of 15 are dead. Okay. That means 8 out of 15 are good. So I want to know the probability that the first 4 you choose are good. This is exactly like that last example on the PowerPoint. So the first one being good is going to be 8 out of 15. Okay. Again, if 7 out of the 15 are dead, then just by pure math, 8 of them are good. So the first one being a good battery is 8 out of 15. The second one being a good battery is going to be 7 out of 14. Okay, because we're assuming without replacement. Okay, the third one being good is going to be 6 out of 13. Hopefully you're seeing a pattern here. And the fourth one being good is going to be 5 out of 12. Okay, and they wanted us to go 4. So round to 3 decimal places would be 0.0 5, 1. Okay. Find the probability that you have to pick 3 batteries in order to find one that works. So they're saying you pick one, you're picking, and you don't get a good one until the 3rd try. So that means the first 2 are no good. So the first one being no good is going to be 7 out of 15. So let's do this one here. First one being no good is going to be 7 out of 15. The second one being no good is going to be 6 out of 14. Okay. Now we want the third one to be good. Well, we haven't used any of the 8 good batteries left. So I have 8 total good batteries. Okay. And out of 13 possible that are left. So it's going to be 7 out of 15 times 6 out of 14 times 8 out of 13. Okay. And then does it say to round to 3? Yep. So that's going to be 0.123. Okay. So that is it for chapters 14 and 15. The rest of the questions will obviously be on chapter 16, and I'll be back with another video on chapter 16.